The world today is awash in data, a vast ocean of information. To navigate this ocean and extract meaningful value, we rely on a systematic approach, the data analytics lifecycle. This lifecycle is a structured, yet inherently iterative, process. It guides data professionals through every step, transforming raw data into actionable insights and tangible solutions. Its primary purpose is to provide a clear roadmap. This roadmap ensures that analytical efforts are not just technically sound, but also strategically aligned with overarching business objectives. Understanding this lifecycle is absolutely crucial for anyone seeking to make successful, data-driven decisions. It guarantees that every analytical endeavor delivers genuine, measurable value. The nature of this lifecycle is flexible, not rigid or linear. While it presents a sequence of stages, the reality often involves revisiting earlier phases as new information comes to light. This adaptability is key to addressing the dynamic challenges inherent in data projects. It allows for continuous refinement and improvement throughout the analytical journey. The importance of this framework cannot be overstated. It is the backbone of successful data-driven decision-making and effective project management. By following its principles, organizations can ensure their investments in data analytics yield significant returns. It provides a common language and methodology for diverse teams. Ultimately, the goal of the data analytics lifecycle is clear: to align every analytical effort with specific business objectives. This alignment ensures that the insights generated are relevant, impactful, and directly contribute to organizational success. It transforms data from a mere collection of facts into a powerful strategic asset. Every successful data analytics project begins with a critical first step: business understanding and problem definition. This is the foundational stage of the entire lifecycle. Without a clear grasp of the underlying business context, even the most sophisticated analysis can miss its mark. This phase involves several key activities. First, it requires clearly defining the business problem that needs to be solved. This isn't just about identifying a symptom, but understanding its root cause and impact. Second, it means understanding the project objectives. What specific outcomes are we hoping to achieve with this analysis? Third, identifying key stakeholders is paramount. Who will be affected by this project, and whose input is essential for its success? Finally, determining the success criteria establishes how we will measure the project's effectiveness. What will a successful outcome look like? The rationale behind this foundational phase is simple: it prevents misdirected efforts. Without a precise understanding of why the analysis is being conducted, resources can be wasted on irrelevant tasks. This initial clarity saves time, money, and effort in later stages. It ensures that every subsequent action is purposeful. The primary outcome of this phase is the formulation of specific, measurable questions. These questions are the bedrock of the entire analytical process. They guide data collection, analysis, and model building, ensuring that the insights generated directly address the business need. They transform vague ideas into concrete objectives. This stage also involves setting the project scope and expected outcomes. Defining boundaries helps manage expectations and prevents scope creep. It clarifies what the project will and will not cover. This upfront agreement ensures that all parties are aligned on the project's direction and deliverables. Once the business problem is clearly defined, the next crucial step is data acquisition and collection. This phase directly follows the problem definition, as the questions formulated in the first stage dictate what data is needed. It's about gathering the raw material for our analysis. This phase involves two primary key activities. The first is identifying relevant data sources. This requires a thorough understanding of where the necessary information resides, both internally and externally. The second activity is the actual gathering of this necessary data. This can be a complex and multifaceted task. Data sources can be incredibly diverse. Examples include internal databases, which house an organization's operational and transactional records. APIs, or application programming interfaces, allow for automated data exchange between different software systems. Web scraping involves extracting data directly from websites. Surveys are another common method, gathering qualitative and quantitative data directly from individuals. Furthermore, external datasets, often publicly available or commercially licensed, can provide valuable context and additional information. The choice of source depends entirely on the project's requirements. Several important considerations guide this phase. We must account for the volume, velocity, and variety of data. Volume refers to the sheer amount of data, velocity to its speed of generation, and variety to its different forms and structures. Managing these verses is critical for effective data handling. Equally important is ensuring legal and ethical compliance in data sourcing. This includes adhering to privacy regulations like GDPR or CCPA, obtaining necessary permissions, and respecting data ownership. Responsible data acquisition builds trust and avoids potential legal repercussions. Following data acquisition, we enter what is often considered the most time-consuming stage, data cleaning and preparation. This phase can consume a significant portion of a data analyst's time, sometimes up to 80% of the total project effort. It is a meticulous and essential step. The challenge here is fundamental: raw data is rarely perfect. It almost always contains imperfections that can severely impact the accuracy and reliability of any subsequent analysis. These imperfections must be systematically addressed before any meaningful insights can be extracted. Common data issues are numerous and varied. Missing values are a frequent problem, where certain data points are simply absent. Inconsistencies and errors can arise from manual entry mistakes or faulty data collection processes. Duplicates, where the same record appears multiple times, can skew results. Incorrect formats, such as dates stored as text or numbers with inconsistent decimal separators, also pose significant challenges. These issues, if left unaddressed, can lead to flawed analyses and misleading conclusions. They are the silent saboteurs of data projects. Key activities in this phase are designed to tackle these problems head-on. Imputation involves handling missing values by either removing records or estimating plausible replacements. Transformation and standardization convert data into a consistent format, making it suitable for analysis. Removal of irrelevant data streamlines the dataset, focusing only on what is pertinent to the problem. Feature engineering is a creative process of creating new variables from existing ones, often enhancing the predictive power of models. This step requires domain expertise and creativity. The ultimate goal of this extensive phase is to ensure data quality and readiness for analysis. Clean, well-prepared data is the bedrock of reliable insights. It allows analysts to trust their findings and build robust models. This meticulous work lays the groundwork for all subsequent stages. With clean and prepared data in hand, we move into data exploration and analysis, often referred to as EDA. The primary purpose of this phase is to delve deep into the data to uncover hidden patterns, relationships, anomalies, and trends. It's about understanding what the data is trying to tell us. A variety of techniques are employed during EDA. Descriptive statistics provide summaries of the data's main features, such as means, medians, and standard deviations. These statistics offer a quantitative overview of the dataset. They help in understanding the central tendency and spread of variables. Data visualization is another powerful technique, transforming raw numbers into easily interpretable charts and graphs. Histograms, scatter plots, and box plots reveal distributions, correlations, and outliers at a glance. Visualizations make complex data accessible and understandable. Hypothesis testing allows analysts to statistically validate assumptions about the data or relationships between variables. This involves formulating a hypothesis and using statistical methods to determine if the evidence supports or refutes it. It provides a rigorous way to test ideas. The outcome of EDA is gaining initial insights and validating assumptions made earlier in the project. This phase helps confirm or challenge initial hypotheses about the business problem. It provides a deeper understanding of the data's characteristics and potential. A significant benefit of thorough EDA is that it informs the choice of appropriate analytical models. By understanding the data's structure, distributions, and relationships, analysts can select models that are best suited to the problem. This prevents the application of unsuitable algorithms. Once the data is understood through exploration, the next critical step is model building and development. This phase involves the core activity of selecting and applying appropriate statistical models or machine learning algorithms to address the defined business problem. It's where the analytical solution begins to take shape. The methods employed can vary widely depending on the problem. Statistical models, such as linear regression, are used for predicting continuous outcomes. Machine learning algorithms encompass a broader range, including classification for categorizing data points, clustering for grouping similar data, and time series analysis for forecasting future values. Several factors influence the choice of model. The data type, whether numerical, categorical, or textual, dictates which algorithms are compatible. The nature of the problem, such as prediction, classification, or anomaly detection, also guides selection. Finally, the desired outcome, like accuracy or interpretability, plays a crucial role. The process typically involves training models on the prepared data. This means feeding the algorithm the clean data set, allowing it to learn patterns and relationships. The model uses this training data to build its internal logic or parameters. This learning phase is fundamental to its predictive power. Optimization is a key aspect of this stage, involving tuning parameters for optimal performance. Models often have hyperparameters that need to be adjusted to achieve the best results. This iterative process of training and tuning ensures the model is as effective as possible. It balances bias and variance. After a model has been built, the next essential phase is model evaluation and validation. The primary purpose here is to rigorously assess the performance and accuracy of the developed models. This ensures that the model is not only working but working well and reliably. Various metrics are used to quantify model performance. For classification tasks, metrics like accuracy, precision, recall, and F1 score measure how well the model correctly identifies different classes. For regression tasks, RMSE, or root mean squared error, quantifies the average magnitude of the errors. The ultimate goal is to determine how well the model generalizes to new, unseen data. A model that performs well only on the data it was trained on is not useful in the real world. Validation techniques ensure the model's predictions will hold true for future observations. This is crucial for real-world applicability. One common technique employed is cross-validation. This involves splitting the dataset into multiple subsets, training the model on some, and testing on others. This process is repeated multiple times, providing a more robust estimate of the model's performance. It helps mitigate overfitting. The outcome of this phase is the selection of the best fit model. This often involves comparing several different models or different configurations of the same model. The chosen model must demonstrate robustness and reliability, meaning it consistently performs well across various data subsets. This ensures confidence in its predictions. With a validated and robust model, we move to the deployment and operationalization phase. The objective here is to bring the analytical solution to life, making its insights accessible and useful in a real-world setting. This is where the theoretical work translates into practical application. This phase involves several key activities. One is integrating the model into existing systems. This could mean embedding it into a business application, a website, or an automated workflow. Seamless integration ensures the model's predictions can be used without manual intervention. Another activity is creating dashboards and reports. These visual tools present the model's outputs and insights in an easily digestible format for stakeholders. Dashboards provide real-time monitoring, while reports offer periodic summaries. They empower users to understand the data. Developing applications for interaction is also common. This might involve building a user interface where decision-makers can input data and receive predictions directly. Such applications make the model's capabilities interactive and user-friendly. They bridge the gap between data science and business operations. The overarching goal of this phase is to make findings accessible and actionable for decision makers. The most brilliant insights are useless if they cannot be understood or acted upon. Deployment ensures that the analytical work directly informs and improves business processes. It closes the loop from data to decision. The final, but continuous, phase of the data analytics lifecycle is monitoring and maintenance. Deployment is not the end, it marks the beginning of ongoing oversight. A requirement for any deployed analytical solution is continuous monitoring post-deployment. The primary purpose of this continuous monitoring is to ensure that the model's performance doesn't degrade over time. The world is dynamic, and what works today might not work tomorrow. Models are built on historical data, and their relevance can diminish. There are several reasons for this potential degradation. Changes in data patterns, often called data drift, can occur as underlying trends evolve. For example, customer behavior might shift, or market conditions could change. The model's assumptions might no longer hold true. Changes in business environments also contribute to model degradation. New regulations, competitive pressures, or technological advancements can alter the context in which the model operates. A model designed for one environment may become obsolete in another. To counteract degradation, several activities are crucial. Regular updates to the model's underlying code or data pipelines are often necessary. Retraining models with fresh, more recent data helps them adapt to new patterns. Recalibration involves fine-tuning parameters to maintain optimal performance. This continuous monitoring and maintenance highlight the iterative aspect of the entire lifecycle. It's not a one-time project but an ongoing commitment. Insights gained from monitoring can even trigger a return to earlier phases, perhaps redefining the problem or acquiring new data. This ensures the analytical solution remains relevant and effective indefinitely.